Okay, hi everyone. So let's discuss with this video the general overview of open interval methods. And to be specific, let's start with the fixed point iteration method. So we have three different methods in open interval methods. Now, instead of having a bracket, uh, we just need to have at least one uh, initial guess to arrive at an approximate solution. So again, we have fixed point iteration for the open interval methods, and then we will also discuss for the next videos the Newton-Raphson method and the secant method. Now, these methods here though doesn't need to know where the root lies, but instead we just want at least one first guess or initial guess, in contrast to bracketing methods wherein we want to first know at which points in the function will the sign changes to define where is the root or where approximately is the root. And also, this is a much more general way to find the root of a given function. Now, with the first scheme, the fixed point iteration method, or also known as the method of successive substitution, if let's say again we have the function f of x and then equate this to 0 to find the roots, we can rearrange, no, or we can manipulate our function so that we have x as in the left side, and we have a function of x at the right side. So this is non-unique. So we have different ways to represent our function in this form. Now I will show you this later. And then the iterative method, we call this an iterative method since we repeat this method in this way. So we keep on substituting the new variable x. No? So this is a rotation of substituting the x on our function on the right side to get a new approximation x sub n plus 1. So we have to write first the iteration function, and the scheme will be such that it will be a cycle of substitution of the new to create of the present approximation to create a new approximation. So let's say we have this function again. We have e raised to negative x minus x. And if we want to find its root, we want to find its function wherein it will be equal to 0. So using the fixed point iteration, we can manipulate this function such that we can transpose this negative x to the other side so that this will become e raised to negative x is equal to x. And swapping these sides, we have x is equal to e raised to negative x. So what is the g of x here? So guys, now the g of x here is this our e raised to negative x. Ayan. So this will be our iteration scheme. Sorry, iteration scheme, but the iteration function for our fixed point iteration. So how do we show this graphically? So the intersection between these two functions, so the function of the g of x and the function x will have an intersection in between them wherein there lies the root. Ano? So let's do this example. No? If we do this example, we will have a tabulation that looks like this. Ano? Sige, let's write this down first. So using our calculator, let's say we have again this function, we have e raised to negative x, so alpha e raised to negative x. And then substitute the initial value. Let's say our initial guess here is equal to 1, for example. So calc 1. So the new guess will become 0.36787. Okay, so from the initial guess, so this is the initial guess, which is also called x sub 0 since the iteration at the iteration 0. The second guess will become this, so 0.3679, and then we keep on substituting this answer. So calc, and then the previous answer will be resubstituted. So this will be our new approximation, and we keep on substituting this value. So calc again, and then answer. So calc answer, keep on substituting this answer. Sorry, calc answer, calc answer, calc answer. Sorry, calc answer, calc answer, calc answer. And then as we can see here, we arrived at this approximation. And then the very last approximation that we will actually get is this 0.5648. Yan. Although, uh, let's just define this later on, no? Actually, this is your x of n plus 1. And this is your, if this is your n, no? So meaning n is the present and n is the future or the next, ano? Or in another, at another perspective, we can say that n plus 1 is your present and n is your previous. Okay, at another perspective. Yeah, sorry. So the visual representation of this, this iteration scheme, this root finding algorithm, you can see it is zigzagging to the true solution, which is this red point. So we start with our initial point and then go through this at this approaching scenario. So let's say we have another equation. Instead of that previous equation, we have x squared minus 3. So the goal here is to make this into x is equal to g of x. So we have to have the left hand side as x only, and then we have to have any function of x at the right hand side. So one example of that is when, let's say, for this case, what we can do is we can add x on both sides. So we have x squared minus 3 is equal to 0. If we add x to both sides, this will become x squared minus, plus x minus 3 is equal to x, right? So this is our new x, and this will be our g of x, for this example. So we can write this in this form, or we can actually write this in this form as well. So we have here x squared minus 3 is equal to 0. And what we can do is transpose this 3 to the other side, and then divide this by x. So divide this by x. So we have x is equal to 3 over x. Yeah. So this is another way of representing our x and our g of x. Okay. Or in another way, though, we could also represent this into this way. I will not show you this anymore. But it could be, there are countless of ways to represent the g of x. Okay, so there is no unique representation of g of x. And the iteration function will be looking like this. So you'll just have to input your present approximation to gain your future approximation. Or in other words, the previous approximation is entered to get the present approximation, and so on. So the question that you have to ask here, so does this tree applicable, or will this tree always work? So the answer is not, no. So there are only a few ways that there are limitations to the fixed point iteration scheme, since for the first case, actually, so the first case here, this first case here is A. It did not approach to this value. It diverges to a different value. Meanwhile, for the second case, it oscillates. So it did not approach the true value. But for the last case, actually it approached. So for this letter C, this iteration function approach to the real answer, which is 1.73 or approximately 1.73. So the problem with the fixed point iteration is that it will not always work, or it will not always converge to the root. And this the function g of x is the main influence of that convergence. Now, what is the condition at which this g of x, this iteration function, will converge. So that is the question, right? So it will only converge if the first derivative of the g of x is always less than 1. No? So what does that mean? If we find the derivative of the function g of x and you substitute the previous and the present x's, no? It should be always within 1, no? So this should be always within the absolute value of this, no? So it should be in between -1, okay, and +1. Okay? So this is the condition at which it will converge to a solution. Now, the graphical representation when the first derivative of your g of x is greater than 1 is that it will diverge. But if it is in between 0 and 1, so meaning it is still within the range of our g prime of x, it will converge, no? Monotonically. And then if it is negative, it will still converge, but it will oscillate. Ayan. But if it is less than -1, it will both oscillate and will diverge. So it will not get a solution. So the conditions that it will arrive at a solution is when it is in between -1 and +1. Its first derivative. Okay, so let's have an example here for fixed point iteration. Okay, so determine the root of x cubed plus 4x squared minus 10, assuming that x sub 0, or the initial guess, okay, is 1.5, and the absolute value of the relative error, or the percentage relative error, is 1.00%. So how should we do this? No? So the goal here in fixed point iteration is we have to manipulate this function in a way that there should be only an x on the left-hand side. So we have x cubed plus 4x squared minus 10 is equal to 0. So there are countless of ways to achieve a solution, or to achieve a g of x here. So what I will do here, I could just factor out this x squared, no? So let's try this. Factor out this x squared. We have x plus 4 and then minus 10. So this minus 10, I'll just swap this to the other side. So this will become equals to 10. And then what will I do here? I will just divide this by x plus 4 first. Okay, so this will become x squared is equal to 10 over x plus 4. And then find the square root of your equation. So this will be equal to x is equal to the square root of 10 over x plus 4. So this will now be our iteration scheme or iteration function, wherein our present approximation is equal to the square root of 10 over x sub n, which is our past approximation or previous approximation, plus 4. Okay, so we will utilize this for our calculator. So we will utilize this. And to calculate also the relative error, so this will be equal to the present minus the previous over the present times 100, which is, let's just say this present is equal to d. So we have d minus c over d times 100. Okay. So the iteration scheme here, we will still tabulate our solutions. So for the iteration counter, iteration meaning we have the repetition, the x value, the g of x, and the absolute value of the percentage relative error. Okay, so for the first iteration 0, we have x here, which is 1.5. Okay, so how do we do this? We have to just utilize our calculators for this. So our function here is the square root of 10, no? Square root of 10 over x plus 4. So we will just input here 10 over x plus 4 inside of the square root. So we will utilize the calc function to substitute the value of 1.5. So 1.5 here. So the value of this is 1.3484. So this is 1.3484. Therefore, this will be our new value of x of n plus 1, which is 1.3484. So for the first iteration, we have the first approximation, that is 1.3484. And then we will continue to substitute this. So calculate again, and then the previous answer is already there. So answer, we have 1.3674. Okay. And then you will do this and so on. No? So this will now be 1.3674. And then for the for the relative approximate error, the percentage relative approximate error, this is now your present and this is your previous to get this one. So this is a blank. Ayan. So calculate this again using your calculator. We have here, let's input here alpha D minus alpha C over alpha D times 100. So calc, we have 1.3484 and then 1.5. Okay, so the answer is 11.24. 30%. And then calculate this again also for the next iteration. Let's go back here. So calc 1.3674 to get this g of x, which is 1.3650. And then calculate the approximate error again. So calc, we have a 1.3674 and then 1.3484. So the answer is 1.3895%. And then for the next one, we have the iteration function. Now substitute again 1.3650 here for the third iteration. So substitute 1.3650. So the next iteration is 1.3653. Okay, and then calculate. Actually, you have to first calculate the approximate error here. So again, this is the calculation of the error, guys, no? So this will be equal to, where's the calculator? Calculator. Yeah. So we have I'll just directly calculate this, 1.3650 minus 1.3674 over 1.3650 times 100. So the answer should be 0.1758. So since this is already lower than 1%, no? So this is our stopping criterion. So this is less than or equal to 1.00%. Therefore, your final answer should be actually this one. No? Kasi we are comparing this together. So this is your iteration. So the approximate answer, the approximate root will be 1.3650. So you can verify this by substituting the value of x to the original function and see if this is equal to 0. Okay? So that will be all for this for this example. But I'll just discuss a little bit about the different ways that you can represent the iteration function for the fixed point iteration. So instead of factoring out x squared, what you can also do is you can transpose this x cubed to the other side and then divide this by 4 and then find the square root, so that your g of x will now be different from what we did last time, no? And if you try doing this again, tabulate this iteration scheme, this x, this g of x, and this approximate error, you will still arrive at the same solution, or at least you can approximate the solution in a similar manner that we did. Although the convergence, no, the time it will converge will be much slower. So this will take maybe at least 4 iterations or 5 iterations more compared to our previous one. Okay, so that's it for this video. See you guys during class. Oh, sorry. Ito pala na-close yung Streamlabs.